And we're solving for A, so I'm gonna get that over there, so I have M5G is equal to M5A plus IA over RL squared. And so acceleration is M5G. Now, in essence, the force that's causing the whole thing to move divided by basically the mass equivalent. M5 is just straight up M5, and then sort of the mass equivalent of the whole, of the rotating bit, which is I over RL squared. And now we plug in Chuck. So that's 5 times 9.8 divided by 5 plus 7.625 divided by 0.5 squared. So that would be 28, so 50, 1 point. Oh, 1.6.
I might need a translator.
Oh, all right. All right, so M5G, all right. So A equals M5G over M5 plus the moment of inertia of the whole rolly thing over RL squared, which is 5 times 9.8 divided by 5 plus 7.625 divided by 0.5 squared.
7.625.
Yep, that's the moment of inertia that we got over there.
And then 0.5 squared.
Yes.
1.38.
Units?
Meters a second squared.
So we now know what the acceleration of the 5 kilogram mass is. We can figure out the angular acceleration of my rotating part. We've already established what the relationship is. I know that alpha is equal to A over R. A we just found 1.38 meters per second squared, and R is 0.5 meters. And so we end up with 2.76 units. It's somewhere around there. That 1.3 was rounded, so this is based on the rounded number.
Second squared.
If you're just leaving it like that, no. But I see where you get that from. You're close.
1 over second squared.
All right, but we can get more sophisticated than that because that might be misleading. If you wrote that, I would give it credit.
To -2.
Oh, that to me that's the same thing.
Oh.
The fact that we took radians in now, radians per second squared. But if you just did 1 over second squared, yeah, that is not wrong. All right, so we went through moment of inertia. We did a mass falling while another object is rotating problem, so we had to bring in the regular Newton's second law as well as the rotational analog. Any questions up to here? All right, we still haven't answered the question that I started out with, is how fast is the center of the rod going when it gets to here? So we're dealing with, well, as long as this is falling, as long as nothing is changing in the overall makeup of this, we have a constant acceleration. My torques are staying constant, the forces are staying constant. We're using the rotational Kate formulas. The constant angular acceleration kinematic equations. However you want to pronounce that. So what are the constant angular acceleration kinematic equations? If you know the regular Kate formulas, just put the rotational analog in there. Or we can take another step back and somebody just tell me one of the Kate formulas.
The change of theta is the initial omega time plus 1/2 alpha t squared.
Delta theta equals, sorry, what'd you say again?
Initial omega
Initial angular velocity, or
t plus 1/2 alpha t squared.
all right, here's one. That. But we don't know time. We don't know how long it's going to take to go around. We could use this to find the time, or we could use one of the other equations, however you want to do it. Now let's go ahead and get all the equations down first. All right, there's one.
Delta theta equals final omega plus initial omega over 2 times t.
All right, 2 down, 2 to go.
Final omega squared equals initial omega squared plus 2 alpha times delta theta.
Okay. And the last one.
Final omega equals initial omega squared.
Just initial omega.
Okay. This is the A, right? Or,
Yep.
okay. Plus alpha
8.
times t.
All right, there we go. So we have the constant angular acceleration kinematic equations right there. I don't know time. I know alpha. Let's go ahead and give an initial velocity here. The initial angular velocity will make 0 radians per second. The angle through which it turns is given in the problem. I mean, I stated what it's doing. We'll have to interpret that. So well, we got our quantities here, so I got delta theta, omega I, omega F, alpha, and time. Alright, so given the problem, what do we know?
Are we gonna solve for time or are you gonna give it to us?
Well, let's put down what we do know first, and then we'll,
We know
Do
alpha,
that. alright,
which is 2.76 radians over second squared.
and we know one other thing.
Initial omega 0 meters per second.
In rotational terms, it's a one-dimensional problem. It's into the board or out of the board. Alpha right here is establishing, since the torque is rolling around like that, establishing out of the board is the positive direction. So I don't really have to have the vector symbol there. All right, so now the rest of the interpretation of, I don't know what the final angular velocity is, I don't know the time, I do know the angle. Through what angle is this thing going to rotate?
Assume 360 degrees.
270.
I wanted to know how fast the middle is going when it gets to here.
270.
270.
All right, now I could write down 270 degrees, and that is not wrong. However, the problem is that we now are dealing with mixed units. And so if you do that, we have to keep track.
We over 2 pi radians?
So converting it to radians, 3 pi over 2 radians. All right, we need to find omega first before we can find the speed of the center of that thing. Which equation should we use? Or we could find time first and then solve for omega, either way.
Has to be the first one.
You want to use this one?
First one, the third one.
Logan, you were asking or saying?
I was saying something, like the initial angular velocity on the board, I think you have it in radians per second? Or is that,
That's radians per second.
okay, then over there it's meters per second.
You are correct, thank you. Bad habits. All right, sorry about that. Thank you for pointing it out. All right, so are we solving for omega straight off, or are we solving for time first?
Omega.
Okay, so we need the equation that doesn't have time in it. That's this one. Recognize this is finding the angular speed, but we know from the context of the problem what the velocity will be. We know the direction. So from this, we have omega final squared equals 0 squared plus 2 times 2.76 times 3 pi over 2. And so my final angular speed is, and someone be kind enough and let's actually not express the answer in terms of pi. Units.
Radians per second?
All right, so that's the final angular speed. What is the final angular velocity? velocity. So we have to bring the direction into it. Is it pointing out of the board or into the board?
Out.
Out of the board.
Indeed. In what we have established at this point as the positive direction. So I can just write 26.0124 radians per second. So I now know what the angular velocity is. I need to figure out how fast this is going at the middle. Well, what's the relationship between speed and angular speed? Yes, Dominic.
For omega initial, is that phi or 0?
That's a 0.
Okay.
For phi, I like, in my mind,
The angle
the
is-
line is
Both different.
more vertical.
Okay.
Now, probably from context, you can get away with not putting the line through it, but I want to differentiate. See, I didn't do it there, but I want to differentiate 2 from 0. All right, so the relationship between linear speed and angular speed. It must have been on the previous screen. Natalie?
V equals RW. V equals RW.
Let's work on the language.
Speed is radius times angular speed.
Yeah, the issue I had was W. What is the letter?
Okay.
Thank you. Yes. V equals R omega. I know omega now. That's 26.0124, if memory serves correctly. R is the distance, because this thing is now down here, the distance from the axis of rotation, so from here to here, which is the same distance it shifted, which is 2.25 meters. So we end up with 258, 59, something like that. Thank you, William.
$58.5279.
And of course, the classic question of, what are the units?
Meter radians per second.
If you wish. Radian optional. So we now know how fast that thing is going. Oh, let's extend this. What the heck? Let's bring back some other memories. Fond memories. Any questions up to here before we extend this? Okay. As the thing comes swinging around, I got my structure right here, and that's sticking out, and it's going to come swinging around as that mass falls. But I got a table right here, and I have a mass sitting on it. We'll make it a frictionless table. And as it comes around, this thing is going to smack into the mass. When it smacks into the mass, this will detach. This mass, why don't we make it, let's see, that was 1 kilogram, let's make this 2.4 kilograms. And let's assume that it attaches at that moment that it hits, and let's assume a perfectly elastic collision. what is the velocity of the 2.4 kilogram mass after the collision? We're dealing with a chapter 8 problem now. Perfectly elastic collision, what does that mean?
Energy's conserved.
Say it again,
Energy's conserved.
more specifically.
Momentum.
Well, yes, momentum and kinetic energy. All right, so it's as if I got two masses here that are going to collide. This one is initially at rest. This one is traveling at 58.5279 meters per second, or meter radians per second if you wish. This has a mass of 1 kilogram. This has a mass of 2.4 kilograms. And I need to know what is the velocity of the 2.4 final. We have three techniques for the perfectly elastic collision. So, which technique do we want to use? One, we end up with a quadratic, but we can do an immediate check of our answer. Two, we don't have the quadratic, and we don't get the check. And three, we shift reference frames. Quadratic, all right. What's that?
Yeah, the first one.
Okay. So, my momentum is, I've got mass of rod, velocity of rod initial, plus mass of box, velocity of box initial, equals mass of rod, velocity of rod final, plus mass of box, velocity of box final. And 1/2 mass of rod, speed of rod initial squared, plus